Okay, so we saw in the previous clip that when we have the second order differential equation d square x dt square plus c over m dx dt plus k over m x equals to 1 over m f of t, we get the characteristic equation lambda square plus c over m lambda plus k over m equals to 0, where lambda is the eigenvalue, and the solution to this characteristic equation is given by lambda equals to minus c over 2m plus minus square root of c over 2m square minus k over m. Rewrite the differential equation as t square plus 2 damping ratio times the natural frequency dx dt plus omega n square x equals to f of t. So using the definitions of damping ratio and natural frequency, we can also write the characteristic equation. So it will be lambda square plus 2 times the damping ratio times the natural frequency times lambda plus omega n square equals to 0. And similarly, the solution for the eigenvalues can be written as minus damping ratio times omega n plus minus square root of damping ratio square omega n square minus omega n square. This is minus damping ratio times omega n plus minus omega n square root of damping ratio square minus 1 equals to minus damping ratio omega n plus minus I omega n square root of 1 minus square of damping ratio. Now, this term minus damping ratio times the natural frequency, this is represented by eta, and this omega n times square root of 1 minus square of damping ratio is represented by omega. So this real part of the eigenvalue, it governs the damping of the response. Okay, so this governs damping of the response, and the imaginary part governs the frequency of the response. So this imaginary part, omega, is known as the damped natural frequency. So let us now extend this concept to a system of two differential equations. So you can think of this as an example problem. So here, the two differential equations that describes the oscillating system are x1 dot plus 0.5 x1 minus 10 x2 equals to minus delta. You can think of this minus delta as a forcing input. So it is similar to f of t that we had for the previous example. And the second equation is x2 dot minus x2 plus x1 equals to 2 delta. So first of all, we want to write this as a matrix equation. To do that, we can rearrange the terms in each of these equations. X1 dot equals to minus 0.5 x1 plus 10 x2 minus delta, and x2 dot equals to minus x1 plus x2 plus 2 delta. So the left hand side is written in the form of a vector minus 0.5, 10, minus 1, 1, x1, x2, plus minus 1, 2, delta. So this is the matrix equation where you can write it as x dot equals to ax plus some beta times delta in this case. Okay, so to find the eigenvalues for this system, you need to solve the following equation. Lambda times I minus A is equals to 0, where I is the identity matrix. So let us first expand this lambda I minus A. So lambda I minus A is equal to lambda 0 0 minus the A matrix, which is minus 0.5, 10, minus 1 1. So that gives us lambda plus 0.5 minus 10, 1, lambda minus 1. And we want to set the determinant of this matrix equals to 0. So lambda plus 0.5 minus 10, 1, lambda minus 1, determinant equals to 0. So this gives us lambda plus 0.5, lambda minus 1 plus 10 equals to 0. Now you can expand it out. Okay, you will find that lambda square minus 0.5 lambda plus 9.5 equals to 0. And again, you can solve for lambda. You know how to solve the quadratic equation. You will get lambda 1 2, so two solutions is equals to 0.25 plus minus 3.07i. Now here you can compare this solution of lambda with the solution we had obtained for the first example, and you can note that minus times damping ratio times omega n is equal to 0.25, and omega n times square root of 1 minus zeta square equals to 3.07. So from these two equations you can find the value of zeta as well as omega n. So either you can go all the way and solve for the eigenvalues and then obtain the value of zeta and omega n, or you could also directly compare this characteristic equation with this characteristic equation, and you'll immediately see that minus 0.5 is equal to 2 times zeta times omega n, and 9.5 equals to omega n squared. So using these two equations also, you can find the values of zeta and omega n. And I have already discussed how the damping ratios zeta and omega n are very useful to describe the oscillatory motion of a system.